Hello and welcome back to Science with John. Today we will be talking about electricity and calculations. Now I know this lesson is quite electrifying, but seriously, we will be talking about something I personally find amazing. So stay tuned to learn about a beautiful formula that might just give you a new perspective on electrical circuits. To start, I'd just like to say that this lesson requires some previous knowledge on the nature of electric circuits and the meaning of voltage, intensity, and resistance. We're now ready to begin, so let's get right into it. This lesson will focus mainly on calculations, and these calculations will be different for both parallel and series circuits. So I thought it would be necessary to teach you, or possibly remind you, about the difference between parallel and series circuits. Let's look at this circuit right here. We see a battery, a light bulb, and a switch. When I flip the switch down, this circuit becomes closed, and the light bulb turns on. The charge flows directly from the battery to the light bulb, and there is only one path for the charge to take. Now let's look at this circuit. We see a switch, battery, and two light bulbs, but it looks a little funny. In fact, we can now identify two paths that the electric charge can take, one leading to each light bulb. This circuit is called a parallel circuit because it has more than one path for the charge to take. We can see this path that leads to this upper light bulb and this path which leads to this downward light bulb. This is a parallel circuit. Now all of this leads to some interesting properties, such as the fact that on a parallel circuit you can remove components and not affect the other ones. For example, if I remove this light bulb, we see that the other one is still on. This is because each component has its own path to the battery. Now on the other hand, with a series circuit, if I remove any component, the whole thing shuts off because I've now broken the singular path the charge has to go on. Now that we can tell the difference between parallel and series circuits, let's talk about voltage, intensity, and resistance, which, again, I am assuming you already know about for this lesson. See, every circuit has a total voltage, intensity, and resistance, which can be calculated. Essentially, when you put together the voltage, intensity, and resistance of a circuit, you get the total voltage, intensity, and resistance. To calculate these values, we use very important formulas. Let's look at these formulas for series circuits. For voltage, we have total voltage equals voltage 1 plus voltage 2 all the way for all the values that you have. In simpler terms, the total voltage of a series circuit is the sum of the voltage at all the circuit components. For intensity, we have the total intensity equals the first intensity equals the second equals all of them. In simpler terms, the total intensity of a series circuit is the same as the intensity at all points of the circuit. For resistance, we have the total resistance equals the first resistance plus the second all the way for all the values you have. In simpler terms, the total resistance of a series circuit is the sum of the resistance of all the circuit components. Let's try using these formulas to find the total voltage, intensity, and resistance of a series circuit. Here I have a series circuit. Let's try calculating the total voltage, intensity, and resistance of this circuit. Let's start with the total voltage. I'm going to take this voltmeter here and measure the voltage at each of these light bulbs, at each of the components. Okay, here we have 7.67 volts. here we have 7.67 volts. And finally, we have the same again, 7.67 volts. Now, if we add all these values together, we will get the total voltage. And if you do that, you get 23.01 volts. Now, let's try calculating the total intensity of this circuit. As mentioned before, the total intensity of a series circuit is the same as the intensity at all points of the circuit. So I can just measure the intensity at any point. Let's do it here. We'll remove this wire, put this right here, and that says 0.77 amps. There you go. The total intensity of this circuit is 0.77 amps. Finally, let's calculate total resistance. If I bring up these light bulbs here, you see that they each have a resistance of 10 ohms. That means I just add 10 ohms 3 times, which is 30 ohms. There we go. The total resistance of this circuit is 30 ohms. But what about parallel circuits? These formulas, but for parallel circuits, are a little more complicated. For voltage, we have total voltage equals voltage 1 equals voltage 2, all the way. In other terms, the total voltage of a parallel circuit is the same as the voltage at all points of the circuit. For intensity, we have the total intensity equals the first plus the second for all the terms you have. In simpler terms, the total intensity of a parallel circuit is the sum of the intensities of each of the circuit paths. For resistance, we have the total resistance equals 1 over the first resistance plus 1 over the second all the way, and all that to the power of -1. Now, this formula looks complicated when you first look at it, but it will make sense soon. Let's take some time to explain it. When I add a new path to my parallel circuit, even though it has resistance, I've still given the charge a new path to go along, which actually makes it faster. A good analogy for this is a highway, where the road is the circuit and the cars are the charge. Say I add a new lane to my highway that is quite thin. That means that not too many cars will be able to easily use that lane, but that overall, the traffic of the highway will go down because there is a new lane. This formula takes this phenomenon into account by inverting the resistance values, i.e., by putting them to the power of -1. Let's try calculating the total voltage, intensity, and resistance of a parallel circuit. Let's start by calculating the total voltage of this parallel circuit. As mentioned before, the total voltage is the same as the voltage at all points of the circuit. So I can just take my voltmeter here and put it anywhere. We see that we have 9 volts. The total voltage of this circuit is 9 volts. Now let's calculate the total intensity of this circuit. As mentioned before, we have to add the intensities of each of the paths. So let's remove this wire first and put this here. We get 0.9 amps. Okay? Now let's do it for this path. We get the same, 0.9 amps. 0.9 plus 0.9 is 1.8. So the total intensity of this circuit is 1.8 amps. Now let's try calculating the resistance. We see that when I click on this light bulb, it has a resistance of 10 ohms. And then this one has a resistance of 10 ohms. Now the calculations for the total resistance are a little complicated, so let's do it together. I have my trusty calculator here and a notepad. So let's first write what we want to write into our calculator. We want to take 10 to the power of minus 1 plus 10 again, because that's the second resistance we saw, to the power of minus 1, and all that to the power of minus 1. Let's find out what 10 to the power of minus 1 is. 10, there we go. 10 to the power of minus 1 is 0.1. So we have now 0.1 plus 0.1, all that to the power of negative 1. Well, 0.1 plus 0.1 is just 0.2 to the power of negative 1. Let's find what that is. 0.2 to the power of negative 1 is 5. The total resistance of this circuit is 5 ohms. So now that we have calculated the total voltage, intensity, and resistance of both parallel and series circuits, let's talk about a relationship between these three values, which is called Ohm's law. This law was set by Georg Ohm, an 18th century scientist. His law states that voltage in volts equals intensity in amps times resistance in ohms. This law works for both types of circuits and is very useful. You can calculate the total voltage, intensity, and resistance of any circuit, and those values will follow this law. Let's just make sure it's right by doing a quick little example. Earlier, we calculated the total voltage, intensity, and resistance of a parallel circuit. We ended up with these values. Now, if Ohm's law is correct, then that would mean that the total resistance, 5, times the total intensity, 1.8, should equal the total voltage, 9. If Ohm's law is correct, then 5 times 1.8 should equal 9. And it does. Now, something that this law is very useful for is finding the value of one variable by knowing two other variables. For example, calculating the resistance of a circuit by knowing its voltage and intensity. In fact, by playing around with the terms of Ohm's law, we find out the following. To solve for voltage, you can just multiply the intensity by the resistance. To solve for intensity, you can just divide the voltage by resistance, and to find the resistance, you can just divide the voltage by the intensity. Let's try and use Ohm's law to solve one of these problems. Say I have this parallel circuit here, and I know the total resistance is 7 ohms and the total voltage is 42 volts. Well, how could I calculate the total intensity? According to Ohm's law, the total intensity should equal the total voltage divided by the total resistance. So we get the total intensity equals 42, the total voltage, divided by 7, the total resistance. That gives us a value of 6. That means that the total intensity of this circuit is 6 amps. Try a more complicated problem. Say I give you this series circuit and say that all 3 light bulbs are identical. I also tell you that the total intensity of this circuit is 0.3 amps and that the total voltage of this circuit is 9 volts. I then ask you, what is the resistance of each light bulb? Well, why don't we start by first finding the total resistance of this circuit, which we can easily do with Ohm's law. According to Ohm's law, the total resistance equals the total voltage on the total intensity. Let's put our values in, and we get that the total resistance equals 9 divided by 0.3. That gives us 30 ohms. The total resistance of this circuit is 30 ohms. But we still haven't solved the problem. We've only calculated the total resistance, not the resistance of each light bulb. Well, if we go back to our circuit laws for series circuits, we know that the total resistance equals the sum of all the resistances. That means that the total resistance, 30 ohms, equals the sum of the resistances of each of the light bulbs. That means that the resistance of each light bulb is just 30 divided by 3, which is 10 ohms. The resistance of each of these light bulbs is 10 ohms. Anyways, I hope that you have enjoyed learning about Ohm's law and other calculations used with electrical circuits. I would also like to take a moment to remind you that what we have talked about today is a very important aspect of physics, mathematics, and also that these calculations will probably turn up on evaluations involving circuits, so it would probably be a good bet to spend time making sure you fully understand and are able to apply them. Before we go, I'd like to give some credit to the University of Colorado Boulder for creating this amazing simulation called Circuit Construction Kit DC Virtual Lab. I'll put a link to this simulation in the description. Let's also do a quick quiz to make sure you've understood everything we've talked about in this video. Feel free to pause the video on this screen. I'll show the answers later. Thanks for watching this episode of Science with John. Bye!